Welcome back. Let us continue the discussion on combustion and thermochemistry. So, we are almost looking at different things under thermochemistry. So, that gives you an idea about fundamentals of basic combustion. So, where we stopped actually now looking at the Gibbs function and all these things. Now, we will continue from there and let us discuss few other things under this thermochemistry, and then we will move to the next set of discussion on kinetics. Now, equilibrium product, that is one important thing. When the reaction takes place, for example, you take an reaction on methane with let us say oxygen, this will give you CO2 plus H2O. Now, when the combustion takes place completely, in the sense there is no excess oxygen or there is no excess methane, then there will be product which will be formed in the terms of major species like CO2 and H2O. If for example, this reaction is not a complete one, then you might get some extra component like CO, O2, something like that. So, those are the some of the intermediate components that may remain in the combustion product. But when you talk about the equilibrium products, actually everything is complete and you can calculate the flame temperature, and which already we have discussed, and these are already detailed out in these previous equations covered in the lectures. Now, you have a constant pressure combustion of propane C3H8 with air, that means it will be combination of oxygen and nitrogen, assuming that the products are CO2, CO and these things. So, the adiabatic flame temperature is T adiabatic and there is major species distribution, and what you can see here is that in the x axis you have equivalence ratio and this is mole fraction and the temperature. Here is the adiabatic flame temperature, this is adiabatic flame temperature. So, this varies along the equivalence ratio and close to 1, which is sort of phi approximately 1 is the stoichiometric condition, and that means in the stoichiometric condition everything is, so the it is neither fuel rich nor fuel lean. So, it is in complete combustion which one would expect, and the temperature rise is the maximum. That is why you can see in the temperature variation it is going up, because once you increase the fuel, that means you increase the equivalence ratio, temperature is going up, but it reaches maximum and then again falls down, because when phi greater than 1, it is a condition which will lead to deterioration of that temperature. Now, other factor is the mole fraction. So, when you look at the mole fraction, some stable products are there. One is that O2 will be consumed like this, then you have a CO formation, H2O formation, CO2 formation. So, these are the some of the distribution, or the distribution looks like in that fashion. Now, one may also would be interested to look at the distribution of minor species, and the minor species are like CO, O, OH, these are all different kind of radicals, CO, OH, O, NO, H. So, these are all radicals or minor species which one can actually look at the distribution along with the phi and see their distribution also, but this is very specific your propane combustion C3H8. If the combustion is different or the fuel is different, this distribution may vary. So, this is a representative figure to show you how the major and minor species they vary when the for varying equivalence ratio. Now, another part of it is the water gas equilibrium, that means So, you need to get some kind of an idea when there is a water remain not in the vapor form, some liquid form in the combustion. So, you can actually find out from a single equilibrium reaction, like when CO is reacting with H2O, you form CO2 and H2. Now, to account for the simultaneous presence of CO and H2, you consider this product and then you can calculate it. So, any arbitrary hydrocarbon if you consider, let us say CXHY, and it burns with air, then you get, let us say this is A times, then you get CO2 CO plus H2O plus H2 O2 plus 3.76 A into N2. Now, for condition phi less than equals to 1, if you have a condition like that, then your CXHY plus A O2 plus N2, this will only becomes BCO2 plus DH2O plus FO2 plus N2. So, that is what you get. So, this is your rich condition, essentially fuel rich condition. Now, another situation which could be possible is the fuel lean condition. This is lean condition, and another possibility is the rich condition, fuel rich condition. So, when there is a fuel rich condition, so that means for phi greater than 1, you expect the fuel is more. So, you do not have any product and CO would be there because fuel is more. So, air is not sufficient to burn that intermediate carbon, so, and you get H2O plus hydrogen and nitrogen. So, depending on your condition, whether it is a rich or lean, you get the different kind of products that will come. Now, A can be correlated with phi, like A is x plus y by 4 by phi. So, for a given fuel, phi is known, then one can find out the rest of the quantities. Okay. So, now we can do that calculation for condition phi less than 1, where C and E they would be all 0, B becomes x, D become y by 2, F become 1 minus phi divided by phi into x plus y by 4. So, that is your essentially 1.69. So, the total number of products, the moles of the products, total number of moles of products in total is x plus y by 2 plus x plus y by 4 divided by phi 1 minus phi plus 3.76. So, that is my total information. So, we can further calculate the mole fraction, that means for x CO2 would be x by n tot, where XCO would be 0, XH2O would be Y by 2 divided by N total, XH2 is 0, XO2 is 1 minus P divided by phi, X plus Y by 4 divided by N total, and X 3.76, X Y by 4 phi into N total. So, these are the all mole fraction that one can get. Now, if you have phi greater than 1, that means it is a fuel rich condition. So, you will have no oxygen which will appear, that means F would be 0. So, to calculate the remaining constant, you can use the 3 atomic balances for C, H and O and water gas shift equilibrium. So, where Kp is partial pressure of CO2 divided by P naught, and this is B dot E C dot D. So, this already we have derived the equilibrium constant, and from there one can find out C would be x minus B, D would be 2a minus, this is an algebra one can carry out on his own and find out these coefficients, how would they look like. Now, once you combine this 1.73, that is this one and this one, you get a quadratic equation in B, and the solution is kind of you will get the. So, this is the equation that, so it is nothing but putting back all this information in this and you get this quadratic equation. So, one you get phi greater than 1 mole fraction for the product, you can estimate the total mole fraction and then rest of the mole fraction for individual element. So, you have CO2, you get CO, you get H2O and then H2, O2 would be 0 and this. So, this is how one can estimate actually the all these things, basically the equilibrium products and all these things. So, that would essentially give you an idea about your thermochemistry, and now we will go to the kinetics, because one of the important things that is required to understand is the kinetics, because kinetics is going to play an important role when you talk about all these reaction system and all these things, because every reaction system, I mean what we are looking at so far is the global kinetics, like CH4 or C3H3 hydrocarbon, when it is reacting with the air or oxygen you get to see, but the in reality the reaction actually goes through multiple steps. So, that is what now we are going to look at now, the kinetics part, and the kinetics part, the way we want to see how these individual reaction steps, and so that will allow you to determine the equilibrium state, chemical reactions and everything. So, now if you assume that the chemical reactions are fast and compared to the other transport processes, then like the transport process, like one of the important process is diffusion. So, when there is a multiple species which are actually interacting in a system, you actually see there is a diffusion takes place, which is an important. Then you have flow field, conduction, so you can locally see these things. Now, most of the combustion cases, so the chemical reaction time scale, which is comparable with that of the flow and the molecular transport processes. So, they are comparable, but certain cases they are not, when especially when you deal with the turbulent cases. So, one need to know or have an idea about the rate of chemical reaction, or the rather the tau chem, which is your chemical time scale. So, one has to know that what would be the time scale that one can get from a. So, reaction rates control also these kinetics, they will control your pollutant formation, ignition, flame extinction. These are the some of the important phases that you will have during the chemical reaction. Now, how you define, I mean, so far we are looking at the single step global kinetics. Now, what we are now going to look at this now, how this single step individual kinetics, like for example, we talk about methane combustion all the time, methane with the air. So, that goes to CO2 and H2O, and if there is a nitrogen. Now, this global kinetics is something which is representative of the methane reaction, but in reality this goes through multiple elementary steps. Now, so important things to know about this elementary reaction. So, that actually occurs in this all these processes in reality. So, now once you look at this elementary reaction, now let us say example you reaction which you describe by OH with hydrogen, which will form H2 and H. So, this is an elementary reaction. So, that means this is a part of a global reaction kinetics of hydrogen combustion. So, where if you look at hydrogen with oxygen, that will form H2O. So, this could be a global reaction where somewhere you get to see this kind of elementary reaction. Now, the following is not, so as I said, this H2O2, this is a global reaction. So, one hand we look at the global reaction and other hand we look at the. So, now let us generalize the thing. For a generic system, you have a fuel which is reacting with, let us say, O amount of oxidizer to produce B amount of product. So, that is a more generic expression. We are not talking about any particular fuel or something or a very specific fuel. We taken fuel and oxidizer. So, what experimentally people have observed that the rate at which fuel is consumed, that means the consumption rate. So, that would be D, their concentration change with respect to time, which would be minus K, let us say G time to the power n oxidizer to the power m. So, that is what you get from this thing, where X denotes the molar concentration of X. So, that means this is nothing but the molar concentration of X, and if you look at the unit, it would be kilomole per meter cube, where Kgt is the global rate coefficient, okay, and where N and M, these are the essentially they are related to the reaction order. Okay. So, now if you look at 2.2, so as per 2.2, it is an nth order with respect to fuel, but if you look at this is mth order with respect to oxidizer. So, the 2.2 the equation says like this, this is the consumption rate and this would be F to the power n oxidizer to the power m. So, nth order or mth order, and overall order of reaction is m plus n. Now, m and n, how one would determine that? So, these are primarily determined from the experimental observation, and they may not be always integers. So, that is one important thing. Now, when you use a global reaction to express the chemistry, so usually it is a black box approach and has limited use in combustion, because most of the realistic combustions are going through the detailed process. So, your global reaction does not provide, so it does not provide the detailed understanding, So, what it actually happening. So, let us one like an example we can see, this is a global reaction for hydrogen oxygen, where hydrogen molecule react with the oxygen to form 2H2O. So, it implies 2 mole here, 1 mole here, produce 2 mole of H2O, which is not strictly always true. In reality, there could be something different, because this is a global system, but there are lot of intermediate species which will form while this global reaction is taking place. So, these intermediate species are important, and that is why one has to look at the elementary reactions or intermediate reaction, elementary reaction steps. So, this will give an idea what are the. So, if we look at it, then there would be multiple elementary reaction like H2O plus O2 can go to HO2 plus H plus O2 would form OH plus O, OH plus H2 can form H2O plus H, H plus O2 plus M would form HO2 plus M. So, this is your equations 2.4 to 2.7. So, these are the different elementary reactions where you can see there is H, HO2, O, OH, and these are forms, and finally you get HO2 and all these things. So, when you talk about all these things, there is this intermediate species or radicals, these are called the free radicals or reactive species. So, that means the intermediate radicals like what you have seen H, O, these are radicals, OH, these are free radicals, rather they are more reactive and they have unpaired electrons, and these radicals are actually quite important, because these are the free radicals which allow this reaction to propagate. So, actually to have a complete picture of the combination of this H2 and O2, more than 20 elementary reactions can be considered. Now, this is not always true that the only hydrogen and oxygen reaction can be defined with only one set of reaction kinetics. There could be multiple, because there are different mechanism. So, now the reaction mechanism, what you call it is that when you look at these elementary steps for global H2 plus O2 to H2O, this is a global reaction. So, these elementary reactions in set of these things are called the reaction mechanism. So, that is essentially required to define or describe the overall reaction. That means, a single hydrogen oxygen reaction can go through multiple elementary steps, and those elementary steps one has to consider. So, this is true pretty much for every fuel that in reality we have which goes through this combustion process, because in realistically every combustion goes through multiple reaction steps. So, now this reaction mechanism may involve few steps or few hundred steps or even 1000 steps. So, one has to look at the state of the art literature to see what are those things. Now, our objective is to look at how we can find out the chemical time scale. So, that is why these elementary reaction steps are very very important, and now using this concept of elementary reactions we want to find out the chemical time scale. Now, the reaction order is constant and can be determined. Another important thing is the molecularity of the reaction. So, it could be unimolar, it could be bimolar or trimolar. So, bimolar reaction for most of the combustion related to elementary reactions are bimolar. That means, there would be A plus B which will form C plus D. So, these are the bimolar reaction, and the rate at which the reaction proceeds, the reaction rate would be d A by dt equals to minus K by molar A and B. So, this is the rate at which this bimolar reaction will proceed. So, that means this kappa bimolar is proportional to function of some temperature and this has some theoretical basis, unlike Kg, rate coefficient of global reaction. So, this is the rate coefficient of global reaction which does not have that theoretical basis, but this bimolar reaction has an theoretical basis, and that comes from the collision theory. But this collision theory of bimolar reaction, that is another important thing, one has to know that this has several shortcomings. So, the approach is quite important for historical reasons and may provide a simple way to visualize bimolar reaction, but uses the concept of wall collision, frequency, mean molecular speed, mean free path. So, the simpler approach is to consider a single molecule of diameter sigma travelling at constant speed v and experiencing collision with identical but stationary molecules. Now, if the distance travelled, that is the mean free path between collisions, is large, then the moving molecule sweeps out a cylindrical volume of this much. So, this is coming purely from the collision theory. So, for random distribution of the stationary molecules with number density n by v, the number of collision one can estimate at the collisions per unit time is n by v sigma square. Now, for Maxwell velocity distribution for all molecules, this ZC is, so this is coming from our statistical mechanics, or where you get this is. Now, when you go to that 2.11 applies the identical molecules. For different molecules, this would be sigma A plus sigma B equivalent to 2 sigma AB. So, my ZC is going to be root 2 n B by V pi sigma square AB B A, which express the frequency of collision of a single A molecule with a, but now for all A molecules one can find out that ZAB by V is nothing but AB by NB by V pi sigma square AB and VA bar square plus VB square, which is to the power half. So, that is what you get. So, I will stop here today and continue the discussion in the next lecture.